Understanding the Don Smith Capacitor Energy Method by Joel Lagace. Introduction. Understanding the Don Smith Capacitor Energy Method. Unlocking hidden energy potential. Energy is everywhere. It surrounds us in forms both seen and unseen, waiting to be harnessed. From the vast electromagnetic fields of the Earth to the latent potential within everyday components, the universe brims with untapped energy that remains largely overlooked by conventional systems. If we can learn to use energy more efficiently, with a focus on unconventional methods, we might unlock pathways to extraordinary advancements in power generation and utilization. This publication aims to explore one such approach, the Don Smith Capacitor Energy Method, an intriguing yet enigmatic system that hints at how energy can be manipulated in ways beyond traditional expectations. Throughout history, pioneers in alternative energy have challenged the boundaries of standard science by rethinking how components behave in unconventional configurations. Figures like John Bedini demonstrated how inductors, capacitors, and other circuit elements could be used in non-standard ways to produce novel results, often aligning with what mainstream science dismisses as impossible. These inventors dared to experiment with what was considered fringe, offering glimpses into energy systems that defy the inefficiencies of modern power grids. Don Smith, like Bedini, left us with fragments of a larger puzzle, provocative demonstrations and tantalizing hints that challenge conventional interpretations of energy transfer, high-frequency behavior, and resonance. One of Don Smith's most fascinating contributions to the field of alternative energy systems lies in his public demonstrations of what can best be described as a one-wire energy transfer system. Using a high-voltage, high-frequency setup, Smith demonstrated how a capacitor plate could charge another plate at a distance, seemingly without any direct electrical connection between them. He referred to this as a mirror effect, figure A, wherein energy appeared to transfer or reflect itself across space. Most intriguingly, he claimed that if you wanted to extract current, you could simply ground the second, or mirror, plate, completing the circuit in an unconventional way. Yet Smith never fully explained this process, leaving much of the inner workings shrouded in mystery. Instead, he often showcased slides of various high-voltage generators, Tesla coils, capacitors, and transformers, hinting at the tools necessary to achieve these effects but without detailing how they all fit together. He even claimed that a single 1F capacitor could produce 1 kilowatt of power, a bold statement that invites deeper scrutiny but lacks sufficient explanation. Figure A. Don Smith Capacitor Demonstration. The goal of this publication is to go beyond Don Smith's surface-level hints and delve deeply into the technical principles underpinning the energy phenomena he demonstrated. We aim to explain how these energy gains might occur from a well-grounded perspective, leveraging both traditional laws of physics and theoretical insights that extend those laws. By exploring high-frequency, high-voltage interactions, resonance effects, electrostatic coupling, and unconventional electromagnetic field behavior, we will piece together a clearer understanding of how systems like Don Smith's could work. Along the way, we will explore the possibilities of tapping into the vast, unseen reservoir of energy all around us, unlocking potential applications that could reshape how we think about power generation and consumption. Let us begin this journey into the heart of the Don Smith Capacitor Energy Method, a journey into a world where energy reveals itself in ways we are only beginning to comprehend. We will follow the clues left by Don Smith and build upon them with rigorous exploration and technical insights. Could his methods hold the key to unlocking untold energy efficiencies? Let us find out together. Chapter 1. The driving circuit, charging the capacitor. At the heart of Don Smith's public demonstrations lies a critical yet often misunderstood element, the driving circuit, the device that quickly and efficiently charges the capacitor, setting the foundation for the rest of the energy system. Whether it was during a lecture or a live demonstration, Don Smith would often dazzle audiences with high-frequency, high-voltage devices, showing various resonance systems that appeared to combine Tesla-like principles of energy transfer with capacitive charge-discharge mechanisms. Observers would eagerly focus on the interplay between coil A and coil B, scribbling notes about their construction, connections, and placement, hoping to replicate what they believed was the magic of his system. But here's the catch: the capacitor doesn't care how you charge it, as long as the driver stage is suitable. This misunderstanding has led many down the wrong path, chasing illusions of magic transformers, instead of grasping the foundational principles of the driving circuit itself. Don Smith's demonstrations frequently highlighted a variety of methods to charge capacitors, ranging from simple, straightforward designs to more elaborate and efficient setups. In some cases, he would use traditional neon sign transformers, NSTs, stepping up the voltage and then driving a high-frequency oscillation. In others, he would demonstrate Tesla coil-like systems with high Q, high-quality factored resonance, emphasizing energy transfer through tuned circuits. At times, he would showcase high-voltage capacitive plates being charged through what appeared to be electrostatic coupling. The sheer variety of charging methods gave the impression of complexity, and many assumed that every coil, transformer, or circuit configuration he displayed was a critical, irreplaceable piece of the puzzle. Figure B. Simplified Don Smith driver stage. However, the truth is more straightforward. Don Smith seems to have been demonstrating different ways he had discovered to efficiently charge large capacitors, each method suited to a specific purpose or efficiency goal. From simple power supplies to intricate high-voltage systems, the underlying principle was the same: find a way to inject energy into the capacitor with as little loss as possible. The focus on his demonstrations often overshadowed the fact that the charging method itself, while important for efficiency, is not necessarily the key to the energy gains he implied his system could produce. A closer look reveals that the real magic does not lie in the driving circuit or the capacitor's charging process, but in what happens after the capacitor is charged. Don Smith often left this part conspicuously absent in his explanations, instead directing attention to his custom transformers and coil configurations. This omission has led to a common misconception among experimenters, that the extraordinary energy output he claimed must somehow come from the transformer configuration alone. Many who attempted to replicate his systems, running loads directly off their high capacitance, high voltage setups, found themselves disappointed, often concluding that Don Smith's claims were exaggerated or outright false. This frustration stems from a misunderstanding of what the driving circuit is meant to achieve. The capacitor is not a power source, it is an energy storage and transfer medium. The driving circuit's purpose is simply to charge the capacitor efficiently, regardless of whether that's done with a simple DC power supply, a Tesla-like resonant coil system, or a modern high-frequency, high-voltage driver using advanced solid-state components. The focus on exotic charging methods has obscured the real question. How does Don Smith's system transduce additional energy into the system after the capacitor is charged, allowing it to deliver the claimed power gains? In this report, we aim to clear up these misconceptions by shifting the focus to the parts of Don Smith's system he left unexplained. While his driving circuits and charging methods are interesting and important for efficiency, they are not the source of the extraordinary energy gains. The real question lies in what happens after the capacitor is charged, specifically in the coupling mechanisms and transduction processes that may allow additional energy to enter the system from the environment. This is where we must direct our attention to uncover the missing piece of the puzzle. In the next chapter, we go back to basics. We will dive deeper into these coupling mechanisms, exploring how capacitors, coils, and high-frequency resonant circuits might interact to produce unexpected results. By peeling back the layers of Don Smith's demonstrations and examining the system from a grounded yet open-minded perspective, we hope to reveal the technical principles behind what he only hinted at. The key to unlocking the potential of his methods lies not in the driving circuit, but in understanding how energy flows and amplifies within the broader system. Let us begin to unravel this mystery together. Chapter 3. Back to the basics, the physics of energy redistribution between capacitors. Let's explore what happens when you take a charged capacitor and connect it directly to an uncharged capacitor. This is a critical exercise to understand how energy behaves in traditional systems, laying the foundation for exploring more advanced energy configurations like those demonstrated by Don Smith. Scenario setup. Pre-charging capacitor A. Imagine we have capacitor A, which is charged to 10 volts. Let's assume the capacitor has a capacitance of 10 microfarads. The energy stored in any capacitor is calculated using the formula. Filled circle energy equals 1/2 times the capacitance times the voltage squared. For capacitor A, the capacitance is 10 microfarads and the voltage is 10 volts. Let's calculate the stored energy. Filled circle first, square the voltage, 10 volts squared is 100. Filled circle then, multiply the capacitance by 100, 10 microfarads times 100 is 10,000 microjoules or 0.001 joules. Filled circle finally, divide by 2, 0.001 joules divided by 2 equals 0.005 joules or 5 millijoules. So, capacitor A starts with 5 millijoules of energy. Connecting capacitor A to capacitor B. Now, we take capacitor A charged to 10 volts and connect it to a second, identical capacitor, capacitor B, which starts uncharged. Capacitor B also has a capacitance of 10 microfarads. Once connected, charge redistributes between the two capacitors until they reach the same voltage. See Figure C. Figure C, capacitor dynamics. Why does the voltage equalize? This happens because of charge conservation. Charge moves between the capacitors to equalize the voltage across them. Since both capacitors are identical, the charge splits evenly, and the final voltage will be the average of the two initial voltages. Filled circle capacitor A starts at 10 volts, and capacitor B starts at 0 volts. Filled circle the average of 10 and 0 is 5. So, after the connection, both capacitors will end up at 5 volts. Energy after redistribution. Now let's calculate the energy stored in each capacitor after the voltage has equalized at 5 volts. The formula for energy is the same. Filled circle energy equals 1/2 times the capacitance times the voltage squared. For each capacitor. Filled circle first, square the voltage, 5 volts squared is 25. Filled circle then, multiply the capacitance by 25, 10 microfarads times 25 is 250 microjoules or 0.00025 joules. Filled circle finally, divide by 2, 0.00025 joules divided by 2 equals 0.00125 joules or 1.25 millijoules. Each capacitor ends up storing 1.25 millijoules of energy. Since there are two capacitors, the total energy in the system after redistribution is, filled circle 1.25 millijoules times 2 capacitors equals 2.5 millijoules. Where did the energy go? Initially, the system had 5 millijoules of energy stored in capacitor A. After redistribution, the system only has 2.5 millijoules. Half of the energy is gone. Why does this happen? The missing energy is not destroyed, it is dissipated as heat during the redistribution process. Here's why. 1. Resistive losses. In a real circuit, the wires and internal parts of the capacitors have some resistance. As charge moves between the two capacitors, the flow of current through this resistance generates heat, which dissipates energy. 2. Electromagnetic radiation. Even if there's no significant resistance, the movement of charge can cause the system to oscillate, similar to how a spring bounces back and forth. These oscillations can produce electromagnetic waves, which radiate energy away from the system. 3. Internal losses in capacitors. Real capacitors are not perfect. They have internal resistance and dielectric losses, energy dissipated within the material of the capacitor, which also contribute to energy loss. Why this matters in advanced systems. When we think about Don Smith's devices, this example highlights why focusing solely on the capacitor's charging process is not enough. Simply charging and discharging capacitors in a traditional way results in significant energy losses. The energy gains. Smith implied in his systems must come from additional energy sources or coupling mechanisms that offset these inherent losses. Chapter 3 continued. The dynamics of energy redistribution and reclaiming the lost energy. In the last section, we saw how half the energy is lost when a charged capacitor, capacitor A, is connected directly to an identical uncharged capacitor, capacitor B. After the connection, the charge redistributes, and both capacitors equalize at half the original voltage, leaving only half of the initial energy in the system. This loss of energy is primarily due to dissipation during the redistribution process, and in a normal circuit, it seems irreversible. However, there's an intriguing possibility if we start to think outside of traditional circuit behavior. What if we introduce a control process, such as flipping the polarity of one capacitor? This opens up a fascinating way to reclaim the energy that is otherwise wasted, and it challenges the limits of what we normally think capacitors are capable of. Let's break it down step by step. Why can't we simply send the energy back? In the standard setup, where we connect capacitor A charged to 10 volts to capacitor B uncharged, charge redistributes until both capacitors settle at 5 volts. At this point, 1. Capacitor A has half of its original charge and is now at 5 volts. 2. Capacitor B has gained charge and is also at 5 volts. The total energy remaining in the system is half of what we started with. But why can't we send the remaining energy in capacitor B back to capacitor A to restore it? The reason lies in charge redistribution dynamics. If you connect capacitor B at 5 volts back to capacitor A also at 5 volts, there is no voltage difference between the two capacitors. Without a voltage difference, there's no driving force to move charge between them. The system is in equilibrium, and no further energy transfer can occur. This is why, in a traditional circuit, we can't recycle the lost energy. It's already dissipated during the initial charge redistribution. The game changer, flipping the polarity of capacitor A. Now let's introduce a twist. What if we use a controller process, e.g., a solid-state switch, H-bridge, or similar mechanism to flip the polarity of capacitor A? This means we reverse the orientation of its voltage, making its positive terminal negative and its negative terminal positive. By doing this, something fascinating happens. Step-by-step dynamics. 1. Initial state kappa at minus 5 volts, cap B at plus 5B. After flipping the polarity of capacitor A, it is now at minus 5 volts, while capacitor B remains at plus 5 volts. Hollow circle, this creates a voltage difference of 10 volts between the two capacitors, since minus 5 volts on cap A and plus 5 volts on cap B result in a potential difference of 10 volts. 2. Discharging cap B back into cap A. When we reconnect the two capacitors with cap A flipped, charge flows from capacitor B back into capacitor A. This is because capacitor B now has a higher potential, plus 5 volts, compared to capacitor A, minus 5 volts. Hollow circle, the flow of charge causes capacitor B to discharge completely to 0 volts, transferring all of its stored energy back into capacitor A. 3. Final state kappa at 0 volts, cap B at 0V. After the transfer, both capacitors are at 0 volts. The key insight here is that capacitor A now holds all the energy that was previously in capacitor B, even though capacitor A ends up at 0 volts. How does this work? Where does the energy go? Let's look at the internal dynamics of this process. 1. Energy in capacitor B. Capacitor B starts with 1.25 millijoules of energy from the previous redistribution step. As it discharges into capacitor A, this energy is fully transferred into the circuit. 2. Capacitor A's role. When we flip the polarity of capacitor A, we effectively give it the ability to absorb energy from capacitor B by creating the necessary voltage difference, 10 volts. This allows all of capacitor B's energy to flow back into the system, but with a twist. The energy is redistributed in such a way that capacitor A ends up with 0 net charge after the transfer. 3. Final energy transfer. The energy from capacitor B is now effectively stored in capacitor A's electric field and circuit interactions. Capacitor A is left at 0 volts, but it has effectively absorbed the full energy of capacitor B's discharge. Why is this process so interesting? This process is extraordinary because it shows how clever manipulation of charge and polarity can allow you to reclaim energy that is otherwise wasted in normal circuits. By flipping the polarity of one capacitor, we 1. Break the equilibrium. Flipping the polarity creates a new voltage difference, allowing energy to flow again between the capacitors. 2. Reclaim lost energy. The full energy in capacitor V, which represents half of the system's original energy, is transferred back into the system, effectively recovering energy that is typically lost as heat or dissipation. 3. Enable full discharge. Capacitor V is discharged completely to 0 volts, which wouldn't normally happen in a traditional setup. This enables its full energy to be used. Implications for advanced energy systems. This process hints at how non-standard energy pathways can be exploited to recover or enhance energy transfer in electrical systems. In normal circuits, the focus is on stability and efficiency, but processes like flipping polarity challenge conventional thinking by introducing controlled instability. This technique could form the basis of advanced systems that 1. Recover lost energy. By carefully managing the flow of charge and flipping polarities at key moments, systems could recover energy that is typically lost during redistribution. 2. Enable energy amplification. If combined with external energy inputs, e.g., resonance effects, environmental energy sources, or electromagnetic coupling, these methods might amplify energy transfer beyond what is possible in traditional setups. 3. Utilize energy storage in cycles. Flipping polarity opens up new ways to cycle energy between components, maximizing the use of stored energy in capacitors or inductors. Final thoughts. This polarity flipping process is a simple yet profound demonstration of how energy transfer dynamics can be manipulated to reclaim or enhance energy flow in electrical systems. While it doesn't violate the laws of physics, it highlights opportunities to sidestep the limitations of traditional circuits. By introducing deliberate control mechanisms, like flipping polarities or using resonance to inject energy, we can explore new realms of energy efficiency and possibly even over unity systems with output greater than input B.